This video is about how we can use counting in order to understand probability better. Probability is the most fun thing that we can study in math. Probability is involved in games and sports and gambling. And probability is involved in making decisions about little things and big things in life. We will look at probability related to dice and cards and casinos and lotteries and sports and all kinds of things, stock market. So how exactly is counting related to probability? Well, let me introduce you to some probability notation. If we see a P and then parentheses A like this, the way that we describe that or that we say that is the probability of event A occurring. That is what that notation means. Here's the formula. The formula to figure out the probability of event A occurring is that we have to count the number of outcomes in event A, and then we have to count the number of possible equally likely outcomes for the situation that we're talking about in general. Now, that's all a little cryptic, so let's look at a particular example. So, question: how many ways can you draw a single card from a standard deck? Well, we would say there are 52 cards in a standard deck. Normally in a standard deck we don't include the jokers, so there are 52 other kinds of cards. And a little bit later I'm going to have you write out a table with all of them so that you'll show me that you actually know. How many ways can you draw an ace from a standard deck of cards? Well, there's 4 aces in a deck. If you didn't know, now you do. All right, so if we wanted to answer the question, what's the probability of drawing an ace from a standard deck of cards? What we would do is we would take the number of outcomes for the event drawing an ace, and that would be 4, and we would put that out of the number of possible equally likely outcomes, which for drawing one card from a deck would be 52 possible outcomes. So 4 over 52 would give us the probability. And we could represent that probability as a reduced fraction, or as a decimal, or as a percent. All right, so let's look at some terminology that's going to be important if you want to understand the language that's used in the problems that we'll be looking at. First of all, there's something called an experiment, and an experiment is an activity with an observable result. For example, tossing a coin. Outcome. The outcome is the result of an experiment. And by the way, if we tossed a coin, an outcome could be that we got heads or that we got tails. If we're drawing a card from a standard deck, the outcome could be that we got the ace of hearts. Sample space. Sample space is the set of all possible outcomes for an experiment. So, for example, let's say our experiment was that we're going to toss 2 coins. The sample space would include heads and heads, heads and tails, tails and heads, or tails and tails. Spinning a spinner. What would the sample space look like? Well, for the spinner that I have shown here in the upper right corner, the sample space would be we could either land on blue, or orange, or purple, or yellow, or red, or green. Event. An event is a subset of a sample space. So for example, for tossing 2 coins, the event could be that I got a heads and a tails, or a tails and a head. Yeah, that would be one possible way to say it. Trials. The number of times that an experiment is repeated. So every single time we do the same experiment, we call it a trial. And you might have heard this language in the news when they talk about, like, for example, when they're testing vaccines. They're doing trials to make sure that the vaccine is safe and effective. Note, I want to point out something. The vocabulary we are using about things like trials is similar to what we used when we talked about simulations, and that's not just a coincidence. All that stuff we did on simulations will be useful to us when we're studying probability. In fact, I got to be honest with you. Probability, it can be pretty complicated, or at least it can be complex. And sometimes having the ability to simulate something is the easier way to get the answer. All right, so we got to talk about something called equally likely, because I said a moment ago that in order to calculate the probability of something, we needed to have we needed to look at all of the possible equally likely outcomes. So what's that mean? Well, in order to use sample spaces to calculate a probability, all of the outcomes in the sample space must be equally likely. For example, if we flip two coins, there is a good way to write the sample space and a bad way for probability purposes. So the good way to write it is that we could either get heads and heads, heads and tails, tails and heads, or tails and tails. Now there is at least one other way to write out all of the possible outcomes of flipping two coins. Another way we could write it is we could say, well, we could get 0 tails or 1 tail or 2 tails. That would adequately describe all of the possible outcomes that you get when you flip two coins. It's possible to get no tails, and it's possible to get 1 tail, and it's possible to get 2 tails. The only problem is that not all of those outcomes are equally likely. If you look in the previous sample space, you can see that it's twice as likely to get 1 tail than it is to get 0 tails or 2 tails. So anyways, there it is. Both ways seem to represent all possible outcomes, but one way is better for the purposes of probability than the other. Let's see here. Oh, in the first one, each outcome is equally likely, each of these 4 outcomes. And in the second one, each outcome is not equally likely. Now, I will tell you this. There is a big debate amongst people about whether the first sample space is correct or not. And I will tell you that there is a really good way to verify which of these sample spaces is correct, and it is using a simulation. And you can either do the simulation manually or using a computer program. And I am hopeful we are going to visit the computer program option. All right, more vocabulary. A random phenomenon. A random phenomenon is a situation in which we know what outcomes can occur, but we don't know which outcome will occur. Interesting. What's that mean? Then there's something called theoretical probability. By the way, let me back up before I leave the random phenomenon. So what would be an example of this? Well, if we go to roll 1 die, we know that we could get a 1 or a 2 or a 3 or 4 or 5 or a 6. That is the sample space of all possible outcomes, and they are equally likely. But we don't know whether we're going to get a 1, a 2, 3, 4, or 5, or 6. So we would call rolling a die a random phenomenon. Theoretical probability. It's the probability of an event that we calculate using mathematical theory. Experimental probability is the probability that you would get if you could repeat the event or the experiment over and over again many times. Now, that introduces us to this thing called the law of large numbers. The law of large numbers tells us that the average of the results obtained from a large number of trials should be close to the expected value and will tend to become closer to the expected value as more trials are performed. What's that mean? Well, what it means is that when I flip a coin, I expect to get heads about 50% of the time and tails 50% of the time. However, if you were to do the experiment right now and you flipped a coin 10 times, I suspect that you're not going to get heads 50% of the time and tails 50% of the time. However, if you flip the coin 1,000 times, you might see that you get very close to heads 50% of the time. and that is due to the law of large numbers. Same is true with other random phenomenon, including rolling a die. If I was to roll a die a few times, I would expect to get, well, theoretically, I would expect to get the number 3 1 out of 6 times, okay? 1 out of 6 rolls, theoretically. But if I roll the die 6 times, I might get a 3 or I might not. And by the way, I could get a 3 more than once. However, if I roll that die 1,000 times, I'll bet you that I get a 3 about 1/6 of the time. Interesting. Okay, so let's take a quick look. I've got a couple simulations for the law of large numbers. We'll take a look at the rolling the die one. Let's see, am I giving it all away? Let me make sure it's a blank slate. Okay, so speaking of rolling a die, we're going to simulate the probability of rolling a 6, which is there's 1 6 on a die, and there's 5 other sides. So we should expect to get a 6 about 1/6 of the time. So I'm going to go ahead and start rolling dice. And I'm going to roll again and again and again. Ooh, look at that. I got a 6 on the second roll. Pretty amazing. So what ends up happening is if I roll again and again and again, in the short run, I'm probably not going to get a 6 1/6 of the time. And strangely, just by some weird coincidence, I'm actually getting a 6 more than 1/6 of the time right now. The thing is, though, is if I was to keep rolling again and again and again, we would see that I'd get much closer to 1/6. And by the way, what is 1/6? 1/6 is about, let's see if I can do this, 1 divided by 6 is about 17%, approximately 17%, or 0.17. So let's take a look at my simulator. Where did I put you? So you can see this green line in my simulator. It's at about 0.17, okay? And what we're expecting is that that if I roll 1,000 times, I should find out that more and more my results are close to that line. So here we go. 3, 2, 1, 1,000 rolls. And here's all my data, and you can see that in the short run I ended up getting 6s much more frequently than 1/6 of the time. But in the long run, the law of large numbers prevailed, and voila, I ended up getting a 6 pretty close to 1/6 of the time after many rolls. Okay. Oh, by the way, something that I want to point out here and that our textbook points out is this is sometimes confused with something called the law of averages. And I don't know if I addressed it, but let me take a look and see. Well, I did not put the law of averages in my presentation, but it is in our textbook. And honestly, there is no law of averages, but it is something that people do refer to and they mistakenly believe. It is described in the textbook on page, what page? 290. And it talks about the non-existent law of averages. And in a minute, I'll talk about, I'll give you an example where I can make sense of what the law of averages is and why it does not apply. Now, the gist of this presentation is supposed to help you understand how to count so that you can calculate probability. And one part of counting is the fundamental counting principle. And there are 2 parts to it. One part is the OR, and in the OR part we say if event A has M outcomes and event B has N different outcomes, then the number of outcomes in event A or B is M plus N. In other words, if we had 2 things like how many ways can I roll a die and let me think about this. Roll a die or roll a coin. Roll a die or toss a coin. Well, if I'm looking at how many ways I could roll a die, there's 6, or toss a coin, that's 2. So 6 plus 2 would give me 8 different outcomes if I was to roll a die or toss a coin. Now, the part of the fundamental counting principle that we use more frequently is the part 2, the AND part. And it says something like this. If event A has m outcomes and event B has n different outcomes, then the number of outcomes in event A and B is represented by m times n. Now, that's a lot of cryptic stuff, just like in the last slide, but I'm going to try to make it more clear because this we really need for probability. Now, it's possible that you may have seen this part of the rule, fundamental counting principle, in your geometry or your algebra 2 class. And I believe that you probably saw it if you took another class like FST or analysis. In order to use this rule, you're going to need to be able to identify events and outcomes. And because of that, I am about to give you some examples of events and outcomes. Also, this rule, oh, by the way, I shouldn't say also, I want to point out that this rule, it's way more powerful than it looks. It's not just if you have two events that occur. It can be used if you have multiple events that occur at the same time. Okay, so let's take a look at some examples. So let's consider the idea of rolling 3 dice. The question we might pose is, how many ways can you roll 3 dice? And then when we are presented with questions like this in math class or in the real world, we should ask ourselves, what are the events and what are the outcomes? Because if you can figure out what those two things are, then you can figure out how many different ways something can occur. So, in this case, rolling each die is one event. So there are 3 events here. And each die can have 6 possible outcomes. If we look at the sample space of a die, it includes 1, 2, 3, 4, 5, and 6. So, to find out how many outcomes you can have when you roll 3 dice, you multiply the number of outcomes of event 1, event 2, and event 3 together. Just like 6 times 6 times 6. And in this case, our answer would be 216 possible ways you could roll 3 dice. Now, let's look at a slightly more practical example. I don't know whether you'll consider this practical or not, but let's try. Instead of dice, we're going to talk about sandwiches. So, a sandwich shop offers specials that includes 4 kinds of sandwiches and 2 kinds of drinks. If we want, how many different specials could be made? Well, in order to answer that question, we have to ask ourselves, what are the events and what are the outcomes? One event is choosing a sandwich type and the other event is choosing a drink. So there's 2 events. There are 4 outcomes for event 1, choosing a sandwich, and 2 outcomes for event 2, choosing a drink. So what we would do is we would multiply the number of outcomes per event together, 4 times 2, and we would get 8 kinds of specials. Let's take a look at another food special situation. So a cafe offers specials that include a drink, a sandwich, and a dessert. They offer 2 kinds of drinks, 3 kinds of sandwiches, and 2 kinds of desserts. And so the question that we'd like to have answered, I didn't write it here, the question we'd like to have answered is, how many different kinds of specials could we have? Or how many different ways could we be presented with a special? And so in order to answer that question, we would then have to ask ourselves, well, what are the events and what are the outcomes? And that would help us to answer this question. How many different specials could one order? So in this one, I think I would like you guys to try to answer some questions. And while we're talking about the cafe special problem or question, I want to point something out to you. Is that I've introduced you to the fundamental counting principle, which allows you to do an easy calculation to determine how many ways some things could occur. But I'd like to point out that sometimes it's not entirely obvious what the outcomes are and what the events are. And so it'd be kind of nice if we had other options for getting to the answer for counting things. And one way that we can do that is using a tree diagram. In the case of the cafe specials, we can have a drink, or we can get a sandwich, and we can get a dessert. And if there's two types of drinks and three types of sandwiches and two types of desserts, we could make a tree diagram that looks much like this, and it would tell us exactly how many different ways we could order a special. Now, in general, my belief is that when working on math problems, especially complex math problems, I think one important technique is to be able to make a picture of the situation to help visualize it. And for the cafe special on the last slide, this is not a bad way to visualize all the possible outcomes. Now, just to kind of tie it all together, I want to point out that if you followed the branches of the tree, you could begin to write out all of the possible specials. And here I have abbreviated the first few. Coffee, chicken, pie, coffee, chicken, cake, coffee, beef, pie, coffee, beef, cake, coffee, fish, pie, and coffee, fish, cake, tea, chicken, pie, and tea, chicken, cake, etc. Okay, so what my goal is this. I would like it so that if you are looking at complicated problems, I would like you guys to have multiple strategies and techniques in order to find the answer. So let's take a look at another interesting kind of problem. It's not dice rolling. It's not ordering food, but it is another situation out of many possible situations where we might like to be able to count how many possible outcomes there are. And one reason why we might, in this particular case, multiple choice test, one reason why we might want to count how many possible outcomes there are, because what if we didn't study? And what if we had to guess? I wonder what the probability is of getting an A on a multiple choice test with 7 questions and 4 choices for each question. What are the odds that I guess, enough correct in order to get an A on the test, or even a B or a C? Well, at a bare min, it would be nice to know how many possible ways could you complete a test like this. Let's take a look. The very first thing we'll do is we'll ask ourselves, what are the events and what are the outcomes? Are the 4 choices on each question the events or the outcome? That's an important question to ask yourself. And I'm telling you this not to feed you knowledge that you're going to memorize. What I'm trying to say to you is this. When you are reading through word problems, whether it's in math class or in the real world, I want you guys to think about, what am I looking at? What does it mean to me? So, are the 4 choices the events or the outcomes? Well, I'm trying to figure out what the events are and what the outcomes are, so I think this is a reasonable question. Are the 4 choices for each question an event or an outcome? Are the 7 questions the events or the outcomes? If I can begin to ask the right questions, then I might be able to find the answers and then get myself to the final answer. And we already know that if we know the number of events, and if we know the events and we know the number of outcomes per event, we can use the fundamental counting principle. So let's proceed. Oh, it turns out that answering each question is an event. Choosing A, B, C, or D as the answer is the outcome for each question. And so, if we wanted to figure out how many ways we could take this test, we would say that we have 7 events and 4 outcomes per event. And therefore, we would take the number of outcomes per event and multiply them together. So 4 times 4 times 4, 7 times. That in this case gets us 16,384 ways to complete this test. And what that means is if you had to guess on every question on this test, the chances of you getting 100% are 1 in 16,384. That's a pretty slim chance of getting 100%. Now, for getting a lower percent, it's a little bit more complicated, so we're going to put that off for now. Okay, another situation where we might want to count, and again, I'm just trying to provide you with a variety of situations just to show you that you might not be able to guess where and how you might use fundamental counting principle because there's so many applications. So here's another situation, license plates. They're typically made up with numbers and letters. Now, in a particular state with a large population, careful decisions must be made about how many letters and numbers are used. Because if you don't use the letters and numbers properly, you might not be able to make up enough unique license plates for all the people. Now, if you think that's a ridiculous situation, I want to point something out to you. We've already run into this problem with area codes, okay? What ended up happening was area codes had a certain system that were used for people's phone numbers all over the United States. And that was just fine when everybody had home telephones, okay? When everyone had just regular home telephones, landlines, there was more than enough area codes for all the people in the United States because there was typically just one phone number per family. When cell phones were invented, all of a sudden a family could have multiple phone numbers. And it turned out, especially in areas like Los Angeles, there was way too many phone numbers for the area codes that we had. And as a result, we had to create new area codes just for the cell phones. So, is the fundamental counting principle useful? Yes. And can it be applied in ways that you would never guess? Absolutely. All right, so back to our situation. What are we going to do? Let's say, take a case where a state allows 3 letters and 3 digits to be used, and they must always be used in the following order: letter, 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 digit, digit, digit. Okay, it's a more complicated problem if the letters and digits could be in any order, and we'll address that later. Anyways, we have this question: how many different license plates could be made? So what you need to do is you need to ask yourself the question, what are the events and what are the outcomes? And then after you have decided what the events are and what the outcomes are, you could then use the fundamental counting principle in order to calculate the answer. And my goal for you is to figure out how you're going to do that. True-false quiz. If you look at a true-false quiz and there were 10 questions there's 10 questions and each one could be true or false, how many different ways could you complete the quiz? What are the events and what are the outcomes? Again, these are the questions we're always going to ask. How many total ways could you complete the quiz? That's what I'd like to know from you. Okay, I'd like you to take a stab at writing out a sample space and using it to count things. And in fact, it's sort of probability related. So, how many ways can you flip 3 coins? I'd like you to write out the complete sample space, and I'll get you started. The very first possible outcome would be heads, 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 or HHH, comma. You complete the rest. Then, using the sample space that you wrote out, answer this question. How many ways could you get 2 tails when you flip 3 coins? There's a little typo there. I didn't put 3. Use the sample space to answer the question. Good luck. Now, the next time we get together, we're going to learn a more advanced way to count things, permutations and combinations.